close the door, or it's too hot?
Well, I guess it's too hot one way or the other.
We did try putting air conditioning on, but it's very loud.
Ah, yeah. We can try, but you think no?
Yeah,
okay,
yeah.
no. And that one doesn't work, obviously.
No.
Okay, let's try to survive then, and if we can't survive, we turn it on.
Yeah. Well, then let's get started. So, hi for everyone online again. Thank you so much for coming. So we're just making this meeting to talk a bit about Gaussian processes regression. So yeah, we thought about inviting some of you as well, since we know this is like a topic of interest and might be useful overall. So I just want to say that in this first session, what we are planning to do is, let me just show you. Okay, just a bit slow. So it's to talk a bit firstly about, I will introduce this more intuitive view of Gaussian processes. So I'll just talk a little bit about as well what is a Gaussian process, and then how can we use them to do regression, and then a little bit about the hyperparameters that we have in Gaussian processes. And so then Maria, in the second part of this meeting, she will talk a bit more about the actual math concepts and proofs that come from this Gaussian processes. So in specific in this session, Maria is going to talk a bit more about this weight space view, so the mathematical concepts in this sense. But we are thinking in the future sessions of then doing the same thing, but from a function space view, and as well to maybe talk a bit about actually in Python, how can we use Gaussian processes for regression tasks. So yeah, so like I said, I'm gonna start by talking more overall about what Gaussian processes are. So then just starting by doing this overview of what doing regression using a Gaussian process is, let's just say that for a given set of training points, so usually is what we have as our data. We assume that there are potential infinite many functions that fit our data. And so what a Gaussian process does is it assigns a probability to each of these infinite functions to be the best fit to our data. So then the mean probability of this distribution will actually be our most probable characterization of the data. So this is what we usually call it as like the mean predicted function. And an advantage of the Gaussian processes is that it also gives us this confidence of our predictions, since this is more like a probabilistic approach. So we have this confidence interval in our regression, a result that you can see here as this shaded region in pink. So this is a nice advantage of what Gaussian processes can give us. And so, as the name implies, when we talk about Gaussian processes, the Gaussian distribution is going to be the building block of our GP. And we are particularly interested in this multivariate case of the distribution, where we just say that each random variable is distributed normally and their joint distribution is also Gaussian. So I'm going to talk a little bit about the concepts of this now. So basically we can define this Gaussian process as a collection of random variables and a finite number of which they have a joint Gaussian distribution. So if we just start by looking at the very basic concepts about Gaussian distributions and how they are defined, we can have, for example, here this example where we have two univariate Gaussian distributions, and they can be described by their mean and their standard deviations, as shown. And actually, we can also describe them together as a multivariate Gaussian distribution. And so this gives us a joint distribution over both variables that is now defined by this mean vector and the covariance matrix in which the diagonal is the standard deviation of each of the univariate distributions. And the other elements are just defining how the variables correlate to each other. So now if we look at it from a regression task point of view by using Gaussian processes, here our goal is to find this function f of x that describes our data. So instead of just assuming, for example, a fixed parametric form of, for example, a polynomial or a line, we can take this probabilistic approach, and we assume that this f of x itself follows a Gaussian distribution. And so the Gaussian process allows us to model this f of x by having a collection of different Gaussian distributions that can be defined by the mean function and this covariance function that we can also call like kernel function. So overall, when we do GP for regression, before we even see any data, we can define what we call a prior of our functions using a Gaussian process. So we often start with a mean function equal to 0. So this is optional just to make the math a bit more simple. And we choose a covariance function. So for example, here in this slide, I'm just showing what RBF kernel is defined by. But I will give a few examples of different types of kernels that we can have in this case. But here I'm just showing an example for RBF. And so with the 0 mean and then RBF kernel, for example, the Gaussian process prior just defines this flexible and smooth distribution over the functions before we even see any data. And then later, when we observe our actual data point, we can update this prior to give us the posterior distribution over the functions. So we basically restrict this joint prior distribution to contain only the functions which agree with our observed data points. So now let's look a bit in more detail to this GP prior and the choice of our kernel or covariance function. So like I mentioned, this kernel controls how correlated the function values at different inputs are, and it essentially just encodes our assumptions about the smoothness and the structure of the functions that we expect from our regression output. So once we choose a kernel and this mean variance, we can sample from this prior joint distribution at any set of input points. So each example that you see here is a vector of function values that follows this multivariate Gaussian, which is defined, like I said, by the kernel that we choose. So again, here I'm just showing an example using an RBF kernel. And so as you can see, each sample that we get looks like a quite smooth function that is drawn from this GP prior. So now I'm just going to show as well a very simple example on how this covariance matrix is calculated for a specific number of x points with a chosen kernel, which in this case is RBF. So for example, if we have 4 training inputs, this covariance matrix can be given by what you see here. And if we choose the RBF kernel, like I was showing before, we end up with a matrix that has this like formulation. And as you can see, you have this the standard deviation f in the diagonal of this matrix. So here as well, we can see this heat map that corresponds to how these values of the matrix varies, corresponding like in with the effect of this difference of these different variance and length scale parameters that we choose. So I'll also talk a bit more about this influence of parameters in the later stages of the presentation. And so, as I said, even though I'm just showing an example for this RBF kernel, there are also a lot of different types of kernels that we can choose for this. But yeah, usually this RBF kernel is one of the most commonly used, since the intuition behind it is that the covariance is quite close to between the variables whose corresponding inputs are very close. So each of the x's that are close, they will have a high covariance, and it decreases with the distance throughout the input space. So usually is a very commonly used kernel for regression. And then here is more just as a note that in reality our observations can be quite noisy. So the actual covariance matrix we end up using can be defined by adding this noise term, sigma of n, which is just the observation noise. And in this example here, this is just homoscedastic noise. So it just means that this noise variance will be the same for all of our data points. So this is why here we have an identity matrix. But we can also have the case where we have heteroscedastic noise. So in this case, we will have a different variance for each of our points. So this is, just wanted to put this here as a note. And so coming back to our main pipeline, now that we have defined our prior based on the kernel that we chose, we can say, in like a very intuitive point of view, that we want to incorporate the knowledge that our training data provides about the function, so our actual observations in the data. So if we have this joint distribution of what we call the training outputs and the test outputs according to the prior, you can see that we have this distribution that is then based on our means and our covariances between the training and the testing points. And so the next step will be that we say that we want to get this posterior distribution, which we can get by restricting our joint prior distribution to contain only the functions that agree with the observed data points that we have. So in probabilistically terms, we just call this operation the conditioning of the joint Gaussian prior distribution on our actual observations. So in summary, if we do this conditioning on the joint prior distribution, we can find what we call the posterior distribution. And as I said, the intuition behind this step is that we want to constrain our distribution on our actual training points. So here I kind of skipped a little bit of the mathematical concepts behind this, but hopefully we can have a better look at it in the next session. But it just means that after we condition it on our observation points, we get a formula to get our, what we call our posterior mean prediction. And so if basically evaluate this posterior mean at every possible x, we get our mean function, which you can see here basically described as this pink function. And this is actually what we want to get in a regression task. So now just a little note in terms of how we actually think of this in terms of machine learning and just computationally. What we want is we want to train we are interested in finding the parameters of our covariance function. And for this, what we need to do is we need to maximize the marginal likelihood to get these parameters of the covariance function we chose. So then again, I skipped a bit of the math, but I just wanted to show here that actually what we end up optimizing is this formula where we are interested in optimizing is the parameters of our kernel, and as well this noise sigma, which is just the observational noise of our data. And so finally, I'm just going to show a little bit about how these parameters that we optimize actually affect our predicted mean function and the uncertainty of our predictions. So then again, I'm going to use the RBF kernel as an example since it's one of the most common ones. And here I'm just showing the effect of the length scale parameter, so this L parameter here. So as you can see, as we increase it, our predictive mean function becomes smoother. So we can think of this roughly as the distance that you have to move in the input space, or so the x, before the function value, so our f of x, can change significantly. And as well, if we look at the effect of this signal variance or amplitude, so this is defined by this sigma of f, we can see how its effect actually affects as well this uncertainty that we have in our data. So a larger variance will make our confidence intervals also become much larger. And just finally, a note as well on this observation noise parameter. In this case, I'm just showing a homoscedastic example. So this just means that the intervals vary constantly for each x. So as you can see here, you can see that if we have no noise term, if it's equal to 0, then our confidence interval in the actual observation point is just 0. And as we increase this parameter, our confidence interval increases as well. And so this was just an overall view, like I said, of Gaussian processes. And in the next session, we would be quite interested in doing a more practical tutorial on how actually to use them to do regression tasks in Python, and as well a bit more about the mathematical background and proofs that comes from this function space view of Gaussian processes. Maybe I'll just stop sharing.
If there are some questions, it's a good time. Or some points for discussion.
Did you find a way to automatically calculate the heteroscedastic noise?
So, more or less, so from what I understood for now, I think actually when we have that heteroscedastic noise term, what we need to do is basically train two different Gaussian processes. So we train one for the heteroscedastic noise, and I think then we need to input it as sort of like prior to the main.
And how do you input like this point-wise noise?
I don't know yet. I haven't seen the actual practical.
Like, so I don't know what method, but for the GPyTorch, there is one, because I looked at it the other day. It is. You don't change the model, you change likelihood, and there's one that assumes you already have the observations, and you basically add those observational noises in to the likelihood as an additional argument.
But for that one,
you have to use like a different GP to optimize the noise, and you get the output from that to use as the input for the first GP.
Yeah. Okay. Yeah.
But it's not an easy way of doing it, unfortunately.
Yeah. So I mean, there is. Can you hear me when I talk, because I have my sound off? Online, can you hear me? Because I don't want feedback. Yes?
Yeah, we can, yeah.
Okay.
Like that.
Biggest noise, Gaussian likelihood. And
Okay.
I think is the way to go. But again, like you said, you have to calculate them first.
So it's like the fixed likelihood.
Fixed noise, Gaussian likelihood.
Yeah.
Which is GPy torch.
I mean, the reason why we wanted to look with Helena into the equations because we were very confused about what to do when your variation in changes with your like time. Usually when we talk about babies, we want to have different noise in early age than late age, and we didn't yet come to conclusion, but we started, okay, let's look at the equations so that we understand what we are doing.
Yeah.
So I don't have the answer to that, Helena as well. So I mean, we see little things here and there that they say, but we don't completely know how they feed the maths yet.
Yeah.
But we are hoping we'll get there. So when we do the second session. So I'm going to describe the same thing that Helena already did, but I'm going to take it a bit more in mathsy way and from a bit different perspective, because it builds a lot on what I'm teaching at machine learning. We don't do any Bayesian stuff, we just do like regression and kernel regression. So maybe to just clarify, so it's done from a different point of view. So we don't really talk about what Helena was describing was that if we have some examples, they should be more correlated if they are closer to each other in terms of like where they are in the feature space. So if we talk age and volume, let's say, so if they're closer to the age, they should be closer in the volume as well, right? So you have higher covariance. If they are far away, it's lower, and this Gaussian kernel basically models the similarity between the features, and from that the similarity between the outputs follows. So it's actually non-parametric model, right? So we don't have parametrization. So I teach that to students, like I decided to do kernel regression because I thought it was the easiest to explain Kernel Trick. I also do support vector machines with them, which uses it for classification, and it's also sparse. Maybe that's more linked to sparse Gaussian processes, actually. So, but it's kind of the same thing, like, but in Gaussian process, you have also this Bayesian treatment that you ignore the Bayesian stuff, all the probabilities you ignore basically when you just talk about regression. So I thought it's nicely kind of built, and also in the book that we had with Helena, they build it from two different perspectives, and one of them is what I'm going to show you now. So this will be lots of equations, so if you can't follow, tell me, or maybe you can give up, I don't know. I warn you, it's hard to follow, and some of the bits, I wanted to kind of work out everything for myself, but some bits I gave up because like I don't have 2 weeks to solve to prove this bit of the theory. So not everything will be completely clear, but I hope that the intuitive ideas will be clear about what's happening mathematically.
Okay.
So I start with just linear regression. So this is not directly Gaussian process, but Bayesian linear regression is very linked to this. So we don't do like Gaussian kernel, but we just do linear regression and how we treat it in a Bayesian framework. Because actually it's not that different, because if you apply kernel trick to that, you will get Gaussian process. And then maximum a posteriori, it's kind of, Helena was talking about likelihood. It's kind of interesting, like likelihood and posterior, all this, it's also in machine learning. You often just have sum of square errors or whatever, and then some other losses. But you often see in the papers that they talk about some probability distributions, and sum of square errors is linked to maximum likelihood. And if you have ridge regression, for example, so if you have penalty on your weights, then it's linked to maximum a posteriori. So I think it's good to kind of understand what this means and where it comes from. So I included that as well, and it's important for optimization of Bayesian regression as well. And of course Gaussian process, but I just didn't get that far in this presentation yet. So, but next time we'll try to finish it. So if we're going to do maths, we have to do notation at the beginning, start with boring things. So we have D features for each sample, And we have n samples. So here I have like brain volume and the baby. So samples are the babies, aged scan is the feature, and the output is brain volume, like the simple thing. And then, so you see that I have X and they have two indices because it's first one is the baby, second one is the feature. So if we have multiple volumes, let's say, then target values is what we, actually this is other way around, right? I'm doing it both ways. It doesn't matter, you can predict which way you want. So yeah, in this case it's age for me. I didn't realize I have it other way around, but doesn't really matter. And samples are babies. So, and this is our linear model, so it's multivariate linear regression. So we have weights, which are the coefficients of the regression, and the features x1 to xd. And then there you can imagine an extra feature x0, which is always 1, which we will be using because then it makes all the equation simple. So this is our prediction model, and then loss function to fit the model. Fit the model means to get these W's, like what exactly they should be. We have sum of square errors, so our given labels and our predicted labels should be the same, or as and this is the rich penalty. So because that's in large ways that's a 2 over fit, so we put L2 norm on it. Basically, further they go from 0, more we penalize them. So this will force the solution to have reasonably sized weights. And this can be a problem. One thing that I found when I started teaching it, that if you put rich penalty on this one, on W0, it's very bad. Because that means that, you know, this is basically the mean of all your data, and you're forcing it to go to 0, so your whole solution will be going away or from. So inside this one is not bad. The thing is, when you apply Kernel Trick, you cannot undo that one, so it makes it tricky, and there is a problem with it as a result that you can actually go to 0 with your function, which is not good. You will see that. But anyway, so that's something to keep in mind. That's why in kernel we put a constant kernel we can add to, so that we model this mean that would otherwise be going to 0. So that's rich. So I will be using matrix notations because we would otherwise write forever. Like, so this is X. It's capital X is our matrix where we put all our features. So it will start with 1, which is for the bias term, and then we have D plus 1 column, so it's for the bias term plus D features that we got, and we have n rows, which is for different babies, so different samples. And then we have column vector for the targets, so that's the output. So it will be n elements, and weight vector has D plus 1 element. So for each feature there is a weight plus for the bias term. And then if we do it like that, the prediction model is simple like this. That's why we do it like that, so that the equations are short. And then also loss function can be written with matrix. So when we have like sum of square errors, actually if you put them to the matrix, then we do matrix transpose times the matrix. And that if you calculate it will give you sum of square errors. And the same for the weight, so that was sum of squares. So if we do W transpose W, if we do multiplication, it exactly gives you sum of squares of the W's. This W is a vector, right? So it's kind of weird that you do column vectors times row vector, right? So you need to realize the dimensions, but because it's 1 times D times 1, you get 1, no, the other way, right? How does it work? I don't know, I confuse myself. Anyway, it should work. All right, what do we do with that? So what's the solution to this? So if we want to solve this, we need to find basically vector W that will minimize this loss. And the way to do it is to calculate the derivatives with respect to W and set it to 0 and see the solution. And there is a closed form solution like this that is not too complicated. I have on the next slide how exactly you get there. I think it's nice to know because it stops being such a mystery how we arrive. So I'll show you in a bit. But basically, here, this thing that maybe reminds you of the matrix in the Gaussian process, and it's actually linked, so that's something we need to invert to calculate a solution. So X transpose X will be D plus 1 times D plus 1, so it's basically square matrix with the size that is linked to number of features that we've got. And then this lambda term, we're basically putting like lambda on the, adding lambda on the diagonal, and that's what gives, that stabilizes the inversion of the matrix. So for example, if you don't have enough data points or if they are too collinear, then this matrix might not be invertible. So that's the problem. And then you might get, if you have lots of noise, not enough data, when you invert the matrix, you get very messy solution. Or if you don't have enough points, you might not even be able to invert it at all because it's not full rank. So that's why if you put lambda on a diagonal, like you add the lambda on the diagonal, you will improve the stability. And depending how noisy it is, how many data points you have, larger lambda, you need to make it stable. So that's the whole point of rich penalty, to stabilize it. So that's that, and here this identity is just to show that we put lambda on all the diagonal points. So this is a kind of derivation of why this works. So it's a little bit tricky because you do derivatives with matrices, but fortunately it works exactly the same as with scalars, so it's actually not very difficult to do. So you just here, like I do derivatives of the first one, or actually like this one, I keep the first one like it's like the multiplication, and do derivative of the second one, which is minus x, and then I do the same the other way around. So I get the other one, and this one is just I get w. So it's like the same as this was squared. So from like x squared or w squared, derivative will be 2w, right? So these very simple rules. So you can easily then get this is the derivative. And actually you could do gradient descent. I am teaching that, and then this would go into the update equation. But because this is so simple, we can just simply set this to 0 and calculate the closed form solution. So only, I mean, it's not like it's easier, because if this is a large matrix, inverting that, you need a numerical algorithm, you can calculate it. So it's a closed form solution, but in fact you need an iterative method to invert the matrix anyway. So well, that's it. All right, so hopefully that makes it a bit less of a mystery where this comes from. Now, so this is an important equation which will keep coming back when we go further. Now I'm going to start talking about the Bayesian framework. So Helena already talked about some of these things. So the prediction model, before we were kind of ignoring the noise in the data. We would just say that y is x times w. And that's probably true for our predicted values. But if we actually want to say like for our measured samples, then we have to add some noise. And then the assumption is that this noise is Gaussian and has constant variance, and I think this sigma n that I have here is exactly the same sigma n you had there, so they match on each other. And then we have to start talking about all the different terms that go into Bayesian modeling. So the first one is likelihood. So it's probability that we observe the data, the samples that we got given our model. Okay, so here our model is linear, so this will be modeled as a Gaussian distribution where mean will be our model, so it will be feature dependent, so we just put the predictive model here, and the variance will be simply this variance of the noise that we've got. And because I wrote it in matrix equation, I put identity here. Right, so this is a joint probability of all the different samples that we've got. I could write it for just one of them as well. But it doesn't really make a difference because we're they are independent when we do linear regression, so it's just multiplication of these probabilities. In Gaussian process, they are not truly independent anymore. Okay, so that's our likelihood, and basically likelihood is linked to this data term, sum of square errors. So we'll see in a bit that when we do all the maths, it will boil down simply to sum of square errors loss when we try to maximize. So we will maximize the likelihood because we want to maximize probability of observing our data given the model. So we need to make the model as good as possible, that this probability of observing data that are generated from the model is as high as possible, right? So when we optimizing maximum likelihood, we're trying to make the model fit to the data. Now, the rich penalty is linked to the prior on the weights. So we can say that was exactly this idea that the weights shouldn't be too large. So if you put the Gaussian distribution with zero mean, and we need to give it some kind of variance as well, P in zero are the most likely, and away from zero, the probability of getting these weights is lower and lower. Okay, and the zero P, when I looked at was linked to this, sigma P to sigma F. Yeah. So that's the amplitude of the Gaussian kernel. It's the same thing. I mean, it's not obvious now that it's the same thing, but in fact, when you look at the equations, it's the same. I don't really know intuitively why, but that's what it is. So we're putting prior on the weights, which tells us that too large weights are unlikely. And depending on how we do this sigma P, we can put it stronger. So if we put sigma P very large, or if we let it go to infinity, then there is no prior on the weights. And we will end up actually doing maximum likely very tiny. All right, so because we are in Bayesian framework, rather than doing some losses or something, we will use Bayes formula to work out the solution. So, I mean, it looks a bit complicated here because you have lots of different things here, but Bayes formula, basically likelihood is y. So this is the observed data based on the conditional parameters of the model, what is the probability of observing the data given the model. But we want to invert it, so we want to say what's the probability of the weights given the data that we got, right? So this is what we know and this is what we want to calculate, right? Because the mean of this posterior probability will be our solution. Okay, and then the kind of the whole distribution gives us the probabilistic solution that is like the whole distribution of solutions. And this is not yet the functions, this is the weights only, right? So this is the posterior on the parameters. I will show you in a bit predictive probability distribution, so we can further work on this to get it to the space of the functions that Helena was showing. But this is just probability for the weights. And because at the moment we have independent samples, so this normalizing constraint, we can ignore it. It's just basically make sure that this posterior is normalized so that the integral adds up to 1. So we will be ignoring that. But for Gaussian process, actually, this posterior is not, this like probability of y is not necessarily constant. I mean, with respect to it, I don't know. So, okay, so here the equation starts being a little bit heavy, and I can't really tell you exactly how they follow from each other because it's too much. Basically, it's possible to work out. So here we have the formula for the posterior, but how do you calculate this? So because this is basically, if we ignore this one, which is just a constant, so this is just a multiplication of Gaussian distribution. So how do I multiply two Gaussian distributions? I mean, it's not that easy, but it's not that difficult either. With some, there is like some, you need to fill two complete square, whatever, to get it, but it can be calculated analytically, and I didn't do it for myself because I didn't want to spend time. But basically, if you do that, so, you know, these are all exponential with some kind of, and you can take a logarithm of it, and then you are just in start working just with these matrices, and that's how you can just rearrange the matrices and to rearrange from one distribution to the other. So that's roughly how it works. But so here I have it written. So my posterior will be this is the likelihood and prior. If you remember how we define it, this is exactly that. We need to multiply them. So let's say that this result after normalization has this mean mu, and capital sigma is the covariance matrix, and this is the solution that you will get if you do that. So so it's like ridge regression, but you see that you have this I, so this is the ridge penalty is weighted by sigma p to -2, and actually this side is also weighted by the noise in the data. So this is prior on the weights, and this is or noise in the weights, you could say, or noise in the, because one over, sometimes they call it precision rather than noise. So because it's like opposite, right? 1 over noise. So this is precision of the data multiplies this part, and precision of the weights multiplies this part. And then because there is also this bit here, if you can actually put it inside, and then you will actually get exactly the expression for the ridge regression, and you see this is the lambda. So it's a variance of the noise divided by variance of the weights gives you the lambda in ridge regression. So that's how they are linked. And the covariance matrix is exactly that. So except that Helena had the matrix K here, is the same. And this is actually covariance matrix anyway for a linear kernel, right? So we are kind of coming to the same thing. And also the mean is basically the weight vector that we would calculate if we were not in Bayesian framework. Which is, so that's exactly the equation we had. And here it's like an example, like what the posterior on the weights might look like. So this is W0, W1, it's just a univariate case. So you see you get this kind of Gaussian, but you see that the two are correlated. That of course, if you change one, you need to change the other. So there is very strong correlation, but there is one direction in which you have much higher uncertainty than in the others. And it kind of makes sense. It will wobble the line a little bit, right? So, and here, so then finally the predictive distribution, this is what we actually calculate in Gaussian process. So it tells you about the result, like your predicted values, right? So to calculate the predicted distribution, what do we need to do? We need to, so this here is the posterior on the weights, and then we multiply it by this likelihood, right? So why is it like that? I didn't write it down and now I forgot. Why is it like that? Anybody knows? All right, so I'll think about it, and I don't know, it's just my brain just went blank. Anyway, so this is the result for the posterior distribution. So when you do that, you basically get, here is your prediction model. So this is feature vector transpose times the Bayes vector. So that's just a linear regression model. And here it gives the covariance. And actually it nicely falls apart into 2 bits. The noise in the data that we were modeling, and this is the uncertainty in the model. Here I have a plot I actually specifically implemented in a NumPy to have something. Where is my cursor? So this is my data. So the red is the fitted linear model, and this little green, that's the uncertainty in the model. And that's the nonlinear part. And this blue, that's noise in the data, and you see that noise in the data is, it's not really easy to see on, yeah, I can see it on my screen, but that is not easy to see. So you need to believe me that the noise in the data, the 95% confidence intervals are parallel to the line because we define it constant. And this, when you see that it's a little bit curved, that comes from uncertainty in the model. Because, I mean, the bias will just move it up and down, but if you have uncertainty in the slope, that will kind of wobble it, so that's why it becomes a bit curved. So that's why even if the noise in the data is homoscedastic, the will not be, how you say, we still have different variances for different points because of the model. Yeah, so that was one thing that we were checking because we were not sure about it, like if we have this homoscedastic noise, whether we would still get the confidence intervals that depend on the features, and so this is kind of reason why.
There's proper names for them, like what they always think of them as intrinsic and extrinsic noise. There's proper names for them.
Okay, I don't know this terminology. Yeah.
I think years ago, Yurong did a talk on it when she used the correct term in that, and I wrote them down. So,
yeah.
I mean, I can share the record if you want.
Say again?
I mean, I can share the record of that if you want. I think I heard most of it.
Yeah, I was just going to say, do you remember you gave a talk a couple of years ago, and you said the correct terms, what the uncertainty in the data and the uncertainty of the model were?
Sorry, I can't hear you.
It's just like if you know like the correct like term for the noise in the data and like the noise
so
of like extrinsic noise.
I think Maria put it on the slides. Is aleatoric and the
epistemic? Yeah, that's right.
Epistemic, right?
So the aleatoric uncertainty would be this one, this noise in the data. Epistemic uncertainty is the one in the posterior because it's in the model weight. Or maybe, I don't know, maybe also this green bit here that you cannot see. Unfortunately, so I'm not really sure, but I think it's in the parameters.
Yeah.
So if you could see my nice shading, then the green one would be the epistemic and the blue one would be the aleatoric. So because we have lots of data, the epistemic one is very small. I had like a volume from CP, and I had to add a lot of noise to them because otherwise I couldn't see the epistemic at all, because it is so much data and for just linear model that it's pretty certain about what the model is, right? Yeah. So it needs to be very noisy for it to be uncertain if you have so much data for just two parameters. All right, and last bit about linear regression is about the maximum a posteriori. So it's the loss that you've already seen something about Helena. So I didn't really show any losses here. So for this Bayesian regression, we can make a loss. I mean, this loss is just for the model. It doesn't like predictive uncertainty or predictive variance. But what it gives us actually optimize these noise parameters as well. So that's why I wanted to put it here so that we can see how it's optimized. So we find the solution, but by maximizing posterior probability of the weight vector W, because that's the parameter of the model. So this is what's written here. So this is the posterior probability. So weight vector based on the data that we've got, so features and outputs, and also the two noise parameters, which are for the N is for the data and P is for the weights. So we want to maximize this posterior probability, and the W, the weight vector, that will make it the largest as the one that we find. So how do we do that? Because we cannot deal with this type of probabilities. We always take like logarithm and a negative logarithm most of the time. And what that does, that we can use the Bayes formula, and it separates things into individual terms that are just added, or so that's easier than to calculate the derivatives. So basically, this is the posterior minus logarithm of posterior, then this is the likelihood and prior, and this is this marginal distribution that we can in this case ignore. So we just have to then fill in this, and because these are all Gaussian, so when you take Gaussian, you will get like the sum of square errors, but not exactly, because there is also the variance, and when you do as maximum likelihood on its own, you tend to ignore the variance because you think it's constant, like in the noise. So it's not really important for optimization because it doesn't change the result. But if you start caring about, I don't know what my noise is, I want to fit it, then you don't ignore it. And actually, if you take logarithm of Gaussian distribution, you get the sum of square error weighted by the precision of the noise. Plus, then you get this term, which is logarithm of the noise, and it's there n times because once for each point. And so you have actually something to optimize also for the noise parameters. It doesn't do anything when you do derivatives, it's 0. So again, this is the same loss as if we did ridge regression loss with this kind of lambda, but you have this extra term that allow you to optimize the noise parameters. So, and that's what usually people they talk about Bayesian regression. You actually don't ignore these noise parameters, but you fit it, and that means that lambda is not just set through cross-validation, but is directly optimized within the loss. And this is, I wanted to show it because we see it a lot when we look at Gaussian process, that you give it some just ranges and then it converges to what it wants. Like what we don't have here because we are still at linear regression is also the length scale, which is optimized. So this is the other two parameters that are there, but the length scale is not here because we don't have kernel yet. But that means that, I mean, I'm not sure I like this Bayesian optimization, then you are not happy with what it converges to, and you kind of don't have a control over it. But in a way, it's kind of framework where everything is optimized and fitted to the data. So if it works well, then it's really good. When I try to check myself, I always felt like it was underfitting the data a little bit, that if you did it with cross-validation, you would select a more complex model, like more non-linear, and this was doing a bit of underfitting. But not always, right? When you were running Gaussian process, sometimes it was overfitting as well. So, yeah, I don't know what the equation is when you put it. I didn't get that far, but maybe it's the one that I showed, but that's what we'll do next time. So, we are running a little bit of so I hope you can kind of follow at least. So I'll just try to quickly, I don't know whether I should leave it for next time. Can you survive another few minutes?
Johnny says he's still patient.
He says what?
He's still patient.
Okay. So,
with you.
so now, so now this was all linear, and how do we do non-linear? Because that's what we're really interested in. So we can build up through thinking first polynomial regression, and we show how it can be understood as linear regression with non-linear feature transformation, and then we can go from feature transformation to kernel trick. And when we do it Bayesian, we get Gaussian process. So nonlinear feature transformation means that I don't take my original features, but I do something with them and I generate some other feature vector. And I have a function that gives me the transformation from my original features to the new features. And one thing that you can do with it, if you, for example, have a linear model, and then you model like quadratic terms. So I have example here. So I have just one feature x, let's say it's the h, but if I then do feature transformation, that I will have three, that will give me quadratic model. Model, the feature x is transformed to 1x because 1 is for the bias and then x is for the slope. Okay, we kind of even in linear regression have this feature transformation implicit. So this is what it means. Then when you apply multivariate linear regression to this, you get like quadratic function, right? So it's a polynomial model. And then you can do the same in multiple dimensions. It's just the equation gets long and ugly. So this is in 2D quadratic and it's already lots of terms. So if you go to like a cubic and you have lots of features, you get, it explodes the number of features you get from it. So you can see that if you do that for high polynomial models, it just overfits really fast and even crashes at some point. So that's why often when you do that, you need to put the rich term to stabilize it as well. So like this is quadratic models with 2 features and you already see that we have 6 terms. So usually feature transformation would usually increase the dimension of the features. I mean, you could do it the other way as well. There is no reason why not, but usually they want more flexible models. So, and then what is really nice about doing like this is that it's still linear function. You just have some basis functions. So all the equations we had for linear regression are exactly the same because you just transform your features and then do linear regression. So what's this? Yeah, so this is sum of square errors basically. This is just transform feature vector, and then I put rich penalty. It gives me the same and it stabilizes the model a little bit. So that's why we do like polynomial rich because it's better. So matrix formulation. So original feature vectors xi are transferred to phi xi. And then I want to make a matrix again, so I will just put these transform feature vectors into the rows of the matrix, and I have big phi instead of big x. And then I do exactly the same. There is no difference. X is explained by phi, and nothing has changed. Okay, so that's why it's really nice because you don't need to do more math. It's the same math. So I have solution for a polynomial rich regression here, and it's the same as for linear. Okay, now the kernel trick. So from the point of view of maths, what we do, so we want a dual representation. So we go to a dual space and I will explain you in a little bit what it is. So now we are more in a feature space because our parameter models are W, so we have as many parameters as there are features. What we're going to do now, we're going to transform into the space where we have as many parameters as we have training samples. Okay, so this phi transposed will basically, it's transformation between this W and A. So W has D plus 1 parameters and A will have N parameters, so as many as training points. And this A is our new dual representation. So, and then we can put it into the prediction model. So this is our prediction model, and if we then put this here, we actually end up with 5 transpose x times 5 xi, and this will be the kernel. So this kernel that we have will be always calculating similarity between 2 points. So in this case is the new sample, so I want to predict at x, so I need to calculate similarity to all the training samples. Okay, so, and basically this dual representation then tells me how should I weigh the similarities to get the output. So basically, if you have Gaussian kernels, so that's what we were having. That so you see, I don't have the amplitude here. So when I'm doing it, it's without the amplitude. That's why it comes somewhere else. But basically, you have I think one when you have equal points, and then as the features go more distant, you get lower similarity. So this is the most intuitive thing that is really important to understand. So when you have this dual representation, you will basically, what it means that your final function is just linear combination of the kernels that are put over your training samples. And this dual representation tells you how you should do linear combination of this kernel to get a solution in each of the individual features. So that's what it does. Okay, so you have lots of Gaussian placed randomly, and you have weights for each of them, for each of your feature vectors, and it will weigh them differently depending what features you put and give you the output. So that's what it is, right? And you cannot, if you choose Gaussian kernel, you cannot easily go back to the weight space, because there is no, you cannot separate it easily. If you start with nonlinear feature transformation, you can make polynomial kernel, and it works like this as well, but you cannot go opposite way from Gaussian kernel back to the weights. At least not in a trivial way, I don't think. But the thing is that you don't have to. Right, so you can define your kernel instead of defining how you transform your features. And it gives you, it's nice for the flexibility. Of course, here you can see why it's a problem if you have lots of training data, because then calculating the output is a nightmare. So that's why there are sparse Gaussian or these approximate Gaussian processes, and actually support vector machines, they have sparsity inbuilt as well. So you have only the support vectors which you use. So I guess the same could be done for regression. Yeah, and another problem, so here you see different length scales. So if I put large length scale, I will get a very smooth curve like that. It doesn't go through the points, even though they are just 3. If I put it just right, it will nicely go through these sparse points and give me nice shape. But if I put it too small, then when it has no data, it will go to 0. Because I'm just doing kind of linear combination of the kernels, and if no kernel has much of a high value in certain area, it will just all be 0. So that's why we have to be careful with these Gaussian processes, that if we don't have data and we make the length scale too small, it behaves weird. Okay, and this is the reason that why, I know, Johnny, I talked with you about that long time ago, and you said that basically what they do, they put a linear kernel plus Gaussian kernel, or constant plus linear plus Gaussian, to kind of deal with this problem. So that's why it makes sense to add kernels together because really this is not really solving, so extrapolation from this is very bad, unreliable. So, okay, so now I'm coming back to what Helena already showed. So you can just put this equation into the rich, a regression loss, and you get this kind of loss that is quite easy to calculate, calculate the results. So basically this is the equation that we get, which is, so this dual representation is this covariance matrix inverted times your output values. So this is the covariance matrix that's just basically we calculate the similarity or apply kernel to all the different pairs of the training samples. So it will be n times n. And from that we calculate. And as well, what is important, this is different when you have windowing by Gaussian kernel, because then you just kind of, it's not the same equation. So it's better fitted than just windowing. And the prediction model, so when we predict, so we have this representation already, dual representation. sample with all the training data. So this is this vector kx, which is vector of similarities of new sample with all the other data. The whole prediction model looks like this. Regression, but same. But it's quite simple when you realize it's easier to understand what to calculate and then understand the math that leads to it. So some examples. So this is kernel ridge regression. So it's the same as mean of the Gaussian process calculating. If you increase the kernel, it's it nicely fits, and when it's too large, underfitting, and eventually it results in straight line. And I think the reason why is because my line is small. And now, and the problem, so now I keep the kernel the same and I'm increasing the ridge penalty, and this is the problem. It's on to linear trend.
We're losing a little bit. I think you're far away from the laptop.
And,
Oh, wait.
Okay.
If you move closer to where Helena's laptop is, I think Teams has started to pretend you're not there. Not your own laptop, Helena's laptop, wherever the audio is coming from.
Okay, I will just share again and see whether that helps. Anyway, I am at the end now. These are the, so when you apply the, why you don't want to go? This doesn't want to disappear now. So when you want to basically apply kernel trick to Bayesian ridge regression, the equation become quite long and it maybe doesn't matter too much. I can't move this thing. But the point is that we arrive to the same. So this is the same as the predictive distribution that we've got. So yeah, I just don't want to go through this equation. I feel it's too hot and maybe I come back to it later. So I just want to go to the result now. So, okay, this is the result. So here we have the predictive mean, and this was the lambda, right? So the predictive mean ended up exactly the same, and the predictive variance looks like this. So it has quite simple equations, the predictive variance, and now that you know what this kx is and a big capital K, you calculate it very easily from the kernel. So what is different that my kernel doesn't have amplitude in it, and this sigma p is in fact amplitude. I didn't really change it, but you can imagine if you put it inside the brackets, you will have here kernel times this amplitude. And if you put it here as well, it kind of rearranges in a way that you can basically see that it's the same thing. So I won't dwell now on the details why it is, but it all fits. Like kernel has the length scale, which I don't have in the equations, but it's the Gaussian kernel, so that's what the length scale is. And sigma p is the same as the sigma f that Helena was showing, and sigma n is the same. And there we can do similar equations as I showed for Bayesian regression to optimize these parameters during fitting, and we'll try to look at it with Helena for next session. And what else is important? Yeah, and we still with homoscedastic noise, which bothers us, and we need to find the solution. So I want to look into equation, how exactly we optimize these hyperparameters, but it's in the book, so we can find it, just run out of time. And heteroscedastic noise, so we'll be looking at it and we'll come back to it. That's it.
For the to the second session.
Were you able to follow? At least partly?
Yeah,
It was lots of equations. Partly. Helena, you were able to follow, right?
Yeah,
because you are
it's
looking at the
easier when
equations
you-
a lot,
yeah.
so yeah. So it's not that hard, but it's a lot. They are long, so it's hard to follow. But I hope at least the main concepts are clear.
I think I got lost a bit around the Bayesian linear regression bit for a bit, but when it went, then I got picked up on part of it again and lost it again. The end screen, I was completely lost on it.
Yeah, I mean, you couldn't help because I just didn't go through it properly. So maybe I will pick it up next time and just focus more on Gaussian process. But
Could you share the slides, please?
yeah,
Of course. We can also share the recording.
yeah.
I'm gonna stop recording.
If you stop the
Yeah.
recording, I will upload the slides into the chat.
That'd be great.
And Helena, you can also upload yours.
Yeah, of course. Yeah.
So I know that this was just